everyone hear me? I think we're not enough, so I technically don't need a mic, but for the setup, I'll use it. So my talk this evening is about AWS Batch. It's titled Planet Scale Workloads, Event-Driven Serverless Pipelines with AWS Batch. I'm Jano Barnard. I'm a cloud and R&D engineer at Cloudvisor. And you can scan that QR code. I'll show it 2 more times, and on the last slide as well, don't worry. There you'll find the slides and some other nice things. All right, so this is a bit of a niche problem, but try to imagine how you would solve it. So, and for the sake of the problem, I've picked a very specific one because I have a bit of a geospatial background, but you could have picked any problem large scale to solve. So the challenge is, it's start of the working day. Your manager wants the building footprints for a specific country. I picked Germany as an example by the end of the day. So how do you do it? So just for a bit of context, Germany is about 360,000 square kilometers. That is a bit smaller than the Northern Cape province, which is funny. And there's about 20 million buildings in Germany, and you have 8 hours to capture all of that. We are going to work on some assumptions. So if you don't have the code ready, tough luck. It's not going to be ready by the end of the day. But let's assume you have the code ready and you can currently process a small area on your local computer at a time. Because we're going to be working here in this scenario with deep learning algorithms, you also need an NVIDIA GPU. And you also have the code to merge 2 areas together. So maybe you can see where this is going. So let's first look at what's not a good solution for this. So Lambda wouldn't work here because Lambda doesn't support graphics cards. ECS could work, but it's a bit on the complicated side. EKS is way too complicated. If ECS is complicated, then EKS is just on another level. SageMaker is expensive and a little bit complicated as well because there's quite a learning curve to get started with SageMaker. And you could go the basic route with building blocks like EC2 and SQS, but that will be a lot of DIY and you don't have the time. If you remember, we have like a working day. So how would we solve this? So enter AWS Batch. Batch is a managed container-based processing and orchestration service for high-performance parallel computing. In plain English, it's a batch processing service. What's cool about Batch, it's super scalable. You can distribute compute amongst thousands of instances. So you wouldn't typically use Batch to do a single, area or a single thing. Batch is all about scaling. The other thing that's cool about Batch is it has this serverless vibe to it. You can do it on demand. You can get compute within like minutes when you need it. Also, it's quite easy to use. It's like ECS, but it's really easy to use. And there's no real learning curve to it. Just a few details that I'll share tonight that you need to know to get started with Batch. All right, so the first of those things that you have to, or choices that you have to make is picking your compute. So Batch itself isn't an instance type or anything. Batch is just the orchestration service around it. So basically you have 3 options that you can choose. You can choose Fargate, EC2 or EKS. EKS, like I said, it's a bit on the tricky side. If you're familiar with Kubernetes, then EKS might be simple and easy to use. But then the other 2 options is Fargate. Firstly, it's the click run done, service. There's no servers to manage. It's less configuration. But if you think back to our problem, one of the prerequisites is we need a GPU. So that leaves us with EC2. So if you choose EC2 as your processing instance, you will get a GPU if you want it. You can get more than 16 vCPUs, a lot of memory, advanced Linux configuration, as well as a custom AMI. If you don't know all the details, it's not important. but just know it's very configurable and you have a lot of knobs to turn. So I can broadly group these into two categories. The first is Fargate. It's very quick to get up and running. It doesn't have those super cold starts that you get with EC2 and EKS. But even though EC2 and EKS is a bit slower to start, you can reuse instances which will become important, and I'll tell you about that a bit more in detail later. Right, so now let's look at the batch components. There's basically 4 components to batch. The first is the job definition, which is a blueprint of the work that needs to be done. The second is the job, which is it's just an instantiation of the job definition. Then there's the job queue, which does what it says on the box. It stores the jobs in the order submitted or not, which we'll get to a bit later. And then the environment, which is the job execution environment. So if you're familiar with ECS or Kubernetes, I'll just go with ECS here. So the job definition is defining the task. In ECS, that's the task definition. Then the job, you can think of as the ECS task itself. It's a task or a subset of work that must be done. If you don't know ECS, and who knows Docker? Anyone here know Docker? So you can think of that as your Docker container. It's a unit of work that needs to be done. Then the job queue you can compare to an SQS queue, like the simple queue service. It's just storing messages in order. And then the environment you can compare to an ECS cluster and an auto-scaling group. All right, so let's dive into these in a bit more detail each. So the job definition exposes a few things that you can set, and later I'll show how this all comes together to solve our problem. But for now, just take note that your job definition, you configure quite a few things. The execution timeout is important here because you don't want your job to keep on running 24/7 if it gets stuck into an infinite loop or something. Then the scheduling priority, because different jobs can have different scheduling priorities. Then there's also something called the retry strategy. The retry strategy is basically, sorry, I shouldn't have advanced. The retry strategy is basically what happens if the job fails. Should it just quit, or do we want to keep on trying a few more times? Is it something that's likely to work if we run it the second time? Then you, of course, need a Docker image. Like I said, the job is just a container that's spun up from like a Docker image. And then if you're familiar with Docker, you would know there's commands and parameters that you can specify to run your container. So you can also do that here. And then some environment variables and secrets, a lot of the ingredients to make this work. And then some of the important things, the job compute resources. So for the specific job definition, you need to tell it how much do you need of the vCPUs, the memory, and if you need a GPU or not. And then there's a lot of advanced configuration that I'm not going to even mention here tonight. So as you can see, the job definition, it's very configurable. You can chop and change as you want. The other cool thing is, as developers, we like things to be versioned, and it's quite cool that you can do this with a job definition as well. So if you make changes, you can always roll back to a previous version. It gets stored in AWS. And then the other cool thing about this is, so a job definition is like a blueprint. You can use the defaults that you set in the job definition, because when we come to the job a bit later, I'll explain how it works, but it's like an instantiation or a copy of the job definition. So basically, you can override anything at that time. So this is just the recipe, but you can make changes later if you want. All right, so now let's focus on the right-hand side first. The job, what it is, or what it consists of. It consists of a job definition. As I mentioned, you can override anything in the job. You also have to specify a job queue when you submit the job. Dependencies up to 20 and array size up to 10,000. I'll get to that also in a minute. But something important here is to look at the job states. So if you think about something that's processing, there's a few essential states that it can be in at any given time. The first state is submitted, which means that Batch hasn't yet looked at it. It's just sitting there and Batch will pick it up soon. The next state is pending, where it's waiting due to a dependency, and we'll get to dependent jobs a bit later as well. Runnable is a big state because that means it's now waiting. Batch has taken the job and it's waiting for compute capacity. So think of it as if the EC2 instance is now starting. The next phase or state is starting, which is, if you're familiar with Docker, it's the Docker pull. It's now pulling your code from ECR usually, and it's starting to get it ready to run. And then running is self-explanatory. It's just going to run your container job. And then you have two exit states, succeeded or failed. So if the job exits with the exit code of 0, it's going to go to succeeded. Otherwise, it's going to go to failed, but it'll only go into the failed state if it's exhausted all of its retry attempts. Just a tip here, if you ever try Batch, just keep in mind that you should leave enough memory for the host instance. Otherwise, your job will be stuck in runnable. You cannot have this virtual container use all your memory. Otherwise, it'll never find a suitable instance to place it on. All right. Now we're getting to some diagrams to show you what it looks like. So I mentioned before, job dependencies is a thing with Batch. You can have up to 20 jobs depending on each other. And I know it's a lot of things to look at the same time, but let's just focus on the top diagram first. So you can see in the top diagram, it's a scenario where the upstream job succeeds. So if you look at it carefully, you can see that it goes through all the states in order, and then it succeeds, and then job B also moves from the pending state, because you can see it's waiting in the pending state, and then it continues its journey once the upstream job went to succeeded. And very similarly, in the bottom example, if the upstream job fails, then you can see that the pending state in job B immediately goes to failed as well. There's no point in trying to run something if you're waiting for something else to succeed, but it doesn't. So that is how dependencies work in Batch. And here is job arrays and more dependencies. So your job can be an array job, and it can be split into 10,000 small parts. Basically what it means is you have a parent job, and then you distribute your workload over like smaller, a lot of instances, and together it gets the processing done. So if we look at the diagram animation, job A is just a normal parent job, no child jobs. Job B, you can see, has a few child jobs from B0 to like N-1. And then between the job B and job C, you can see there's an end-to-end dependency. What that just means is that if job C0 wants to run, it only depends on job B0. So what it means is, and you can see in this step, some of them can still be running, and then it's like sibling jobs can already proceed with the next step. And then in job C to job D, you can see there is just a normal dependency. All of the child jobs in job C must complete before job D can start. And then when we get to the animation in job D, you should look at the sequential dependency. So that just means that the first child job is going to be the upstream job, and job D1 can't go ahead without job D0, and so on. And then right at the end, we just have a normal dependency again. So you can see Batch is very powerful, and all of this is managed by Batch. You can just tell it what should depend on what, and it will handle the rest for you. So it's very powerful, very cool. It hides a lot of the complexity, and that's why it's so easy to use. So now this is a big question. How do we differentiate between child jobs? Because something interesting is all of the child jobs run the exact same code, like exactly the same. The only difference there is environment variables that get set by AWS. And the biggest and most important one is that top one there, AWS Batch Job Array Index. So that just means like what job are we looking at? Is this 0, 1, 2, 3, etc. So that is going to be your index that you use to determine inside your code, where am I? What is the specific, child job that I'm currently running in? And then if you want to get the total number of child jobs, you can look at the AWS Batch job array size environment variable, which will be the size of the parent array job. And there's a lot of other ones, but I just wanted to explain how you differentiate between them. All right, now the job queue. So the job queue, you can specify a few things as well, and I'll get to the nice animations in a moment. But for the job queue, you can specify the queue priority, as well as the scheduling policy, which we'll see in the animation shortly, and then the compute environment or environments, because you can mix and match. It can become very complicated. You can have multiple compute environments, which I'll explain in a minute, and then the compute environment order if you have multiple of them, as well as the job state limits, which I won't go into detail. But the scheduling policy is quite cool and it's very useful because it addresses a real problem. Who here has heard of FIFO queues and know how it works? Okay, so there's a few people. So FIFO queue is the simplest, first in, first out. So that just means if you put 10,000 jobs in the queue, it's going to go in order 0, 1, 2, 3, etc. And that's the order it will process in. But what if you have multiple users? Let's think a bit. Maybe there's an application with users submitting multiple requests. Maybe it's inside your company, different departments. How do you share equally between those guys? So to do that, you can use the equal weight policy to share fairly between them. So in that bottom example, you can look at the green and the blue jobs. So imagine it's two different people. It won't just go, because green is technically the front of the queue, it won't take all of green at once. It will go green, blue, until all the compute power is in use. And then it'll wait and clean up, as soon as job finishes, it will take more. And that is why, as I mentioned earlier, why you want to pick an instance type which can be reused, because those instances don't shut down. Each of those little blobs in the compute environment, it's like an EC2 instance in our example. So each of those instances can stay up and be reused for the next job. You just have to make sure that you clean up after running code on there so that you don't fill up the storage over time. All right, so then there's two more. It gets a bit more advanced. So then there's the priority scheduling policy, where you can see, well, you may or may not see, it's very small, but trust me, there's two priorities in there. Some of them have red, and I believe the red is 1, and the yellow is 2. So you can see it picks all the highest priority first, and then it starts with the lowest priority, even though the lowest priority is at the start of the queue. And then the last scheduling policy we're going to look at tonight is the compute reservation one, where you always keep an extra space just in case someone comes and joins the queue a bit later. So in that example, you can see it, even though there's 4 jobs submitted by the green user, it still reserves leaves one instance open, so that if another user comes along later, then there's immediately space. Because if we don't leave that space, it means that that user has to wait until a green job is done, and then it will only load it. Even if you share it fairly, if there's no instances available in the compute environment, you can't start running immediately. All right. And then Batch also has something called resource-aware scheduling. What that basically means is that in the case where your external resources cannot keep up, because Batch can really scale. It can really scale. Basically, the limit is not the sky in this case, but your AWS quota. So how many EC2 instances you can launch, or how many vCPUs, I should say, that's basically your limit, and how many there are available in a specific availability zone or whatever you've configured it to run. So in that case, you can use resource-aware scheduling, and you have two types of resources here: replenishable resources and non-replenishable resources. In the case of replenishable, think of third-party license tokens. You can borrow it and you can put it back once processing is done. The same with database access bandwidth. You don't want to overwhelm a database. Especially if you're working with third parties, that's where the third-party API throttling also becomes an issue. So then you can say, hey, I'm at max, even though there's more instances available, don't launch more of this specific thing. Let's say you're talking to two different APIs, then you can say, if user A and user B are talking to two different APIs, and that's sort of the bottleneck, then you can have them as separate resources that replenish on their own. So you can then go full scale, but if both users want the same API that you don't have control over, then you might want to scale down. Non-replenishable resources, if it's used, it's used. That's also an option here. Right, now I get to the brains of the operation, the compute environment. So the compute environment allows you to set a few things. One of them is an instance role. It just means that your EC2 instance gets the permissions that you attach to that role. So if you want to reach S3 or any services, you have to make sure it's in that role. Then the next thing is the spot instance configuration, because we're looking at EC2 for an example. You can also configure your spot instances. And then the minimum and maximum vCPUs, which basically means, is it going to scale down to 0? If you set it to min 0, then it can scale down to 0. And what is that upper limit? What's the max number of concurrent instances that you can run? That's your max vCPUs. Well, that's determined by the max vCPUs rather. Then the allowed instance types. So, and I'll reiterate that a bit later. AWS recommends that you don't just say, here's a single instance type, because what if there's a lot of other people using it and it's not as highly available at that point in time? Then you can always fall back if you have multiple instance types defined, then you can fall back onto other ones. And then the instance allocation strategy. If you have multiple instance types, this becomes a thing, and we'll look at that in a bit more detail now as well. And then the EC2 launch template. For those familiar with EC2, it's just configuring bells and whistles that comes with EC2, all the configuration. You can also set up a lot of VPC configuration here. Do you want to run in private, public, subnet, a lot of things. And you can also do custom AMI if you want your virtual machine or your hard drive to boot with a specific configuration. That's where you will set that. And like I mentioned earlier, you have EC2, Fargate, and EKS as options for your compute environment. That's been the setup since, I think, whenever Batch launched. I can't remember exactly. I think it was 2017 or something. And then more recently, AWS also added a service environment. And there you can only set the number of instances, nothing else. I think they'll probably expand it a little bit more over time, but that is if you want to use SageMaker. So if you want to do AI stuff specifically, that's what you can use. And why don't you just use SageMaker directly, you might ask? Because Batch, as you've seen, does all the orchestration for you from the start to the end. It will handle retries for you. It will handle all of those dependencies, all of the concurrency limits, all those things. So that's where SageMaker can also be used. Okay, so now the instance allocation strategy. Because you can have multiple options in your, let's call it, library of instances that can be used at any given moment to be added to this compute environment. So the first one is best fit, and best fit progressive, the first and second one, therefore EC2 on-demand instances. And if you're looking at Spot, you're going to look at the other two, the bottom two. But let's first look at best fit. Best fit basically selects the cheapest instance type, and it doesn't switch when constrained. So what it just means is that if you select best fit, and let's say you're using G4 DN 2x large or whatever, and it runs out of those instance types, or for some reason you can't get more of them, then it's not gonna switch automatically, even if you have other options available inside your compute environment. Then best fit progressive, it will still go with the cheapest instance type first, but if capacity becomes constrained on that instance type, it will automatically switch over to a better instance type. Then for Spot, you can use the Spot capacity optimized and Spot price capacity optimized options. For those not familiar with Spot, it's just a throwaway instance which you can use for a short time, and it can get interrupted at any time. It's very cheap. So for capacity optimized, it's fewer interruptions, a bit more expensive. You pay for that premium for that option to have it interrupted less. Capacity optimized, or price capacity optimized rather, it's a low price and it's generally an acceptable capacity. All right, so we've covered all of the sort of pillars of Batch. Now let's look at storage on Batch. Where do you store your data? So EBS is the default place to store your data. It's good for single instances, one EBS volume per instance. It's relatively slow. It's also limited in size. Well, it's up to 16 terabytes, I believe. That's the default. Then instance storage, that's my favorite, to be honest. I always use that as scratch storage. It's ephemeral, meaning if you shut it down, your data is gone, but it's very fast and it's limited in size. What it means is that basically if you select an EC2 instance type that comes with an instance store, then you can use it. You can format it and you can keep on using it, and it's nice for scratch storage. So temporary storage before you save it permanently, that's a nice option to go for. And based on some tests I've done before, that's about like 10 to 15 times faster than EBS under like normal configuration. So it's really nice to use. Then if you want to store on a network drive, you can use EFS or FSX for Lustre, for example. There you have a shared data pool. It has high throughput and it's good for sharing data between instances. So if you want to, read from the same place, that's also a nice option for you. And then S3. This, I would say, is your permanent storage type. You store the data remotely as objects, and it's basically unlimited in size. So that's sort of your wealth of options you have for storing data. Okay, then how do you keep the costs down? So let's look at some FinOps things here. The first is savings plans. So if you intend to use your instances for quite some time, usually a few years, then you can commit to a certain capacity and you can save when your batch processing schedule is known. But obviously, if it's going to be spiky, then you might want to hang on a bit before you commit to that. Spot instances, as I've already mentioned before, if your processing is, I would say, thumbs-up value less than 30 minutes in runtime or duration, then you can use this and it will save you a lot of money, and it's good for short interruptible workloads because at any time it can be shut down when those instances are going to be used for full paying customers, if I can call it that. And then cost tags, or cost allocation tags rather, that's my go-to way, and I think it should be everyone's go-to way for tracking expenses. So you can use that to track your dollar cost per job by using cost allocation tags and the cost and usage report, which I think AWS renamed in the last 2 years. So that's your go-to. Also, the cool thing here is if you have multiple batch jobs running on the same instance, because that is possible, then you can also get your cost per job. So you can really go fine-grained here. Okay, then you want to monitor your batch jobs, especially at this scale. So the default log store is going to be CloudWatch logs. You can view your batch logs there. You can set up alarms based on things like the log group metric filters. You can do all the things that you would expect from CloudWatch. And then there's also something that you can look at in Batch called Container Insights. and that will give you all the metrics like CPU, memory, disk, network utilization, job instance counts, and it's ready for CloudWatch dashboards. So that's your toolkit if you want to monitor, and you definitely should if you're going to run hundreds or thousands of concurrent EC2 instances. So we've talked about when and why and all of those things, why batch is good, but now let's look at when you shouldn't use batch, because like every AWS service, there's trade-offs. It's great for high performance compute needs, but it's not the solution to everything. Two things that I can point out. Bad fit number one, short jobs. If it's some processing that's going to run for a few seconds, even a few minutes, then the overhead to schedule the job is probably going to be more than the job's runtime. In that case, you can consider using Lambda or something else. The other case is for real-time jobs. So batch is a scheduler and it needs some time to process requests. So in that case, I would use ECS or EKS instead, because what batch does, it has a mechanism which picks up jobs, and basically it has these 2-minute intervals. And if you submit the job just before the cutoff, then you're lucky, it's going to pick it up basically immediately. And if you miss that cutoff, then you have to potentially wait a full 2 minutes for your job to even be picked up and considered for running. So it's really not good for real-time job use cases. Okay, let's look at a basic architecture diagram. This is how I would integrate batch if I have to integrate it in a basic web application. You can imagine your user connects to the front end, which is hosted on Amplify, and then API Gateway is the backend, hosts the backend, and API Gateway runs on Lambda. And then S3 and DynamoDB is basically your two storage types here, and that is accessible in the API Gateway Lambda as well as in batch. So you can imagine that you update the progress from batch into DynamoDB, and you save your permanent files in S3, and your API can query that or something like that. So that's basically how you can use it. So for integration, batch can be triggered from Lambda, as I mentioned, in API Gateway. It can be triggered from anywhere, but that's a good integration. Then batch also emits EventBridge events on job status change. And this is super cool because it means you don't, if you want to know if one of those 1,000 jobs is complete, you can just listen for an event. You don't even have to have any code inside your code running on batch that listens for anything or updates the database. You can just have an EventBridge event that you listen for. Batch publishes that automatically. And if you listen for that event, you can trigger a Lambda function when a batch job or child job finishes or fails or whatever. And you can do logical stuff like update your database, like progress bar, things like that. Also, because I mentioned it before, batch is sort of serverless. It works quite well with serverless services like S3, think DynamoDB, those type of things. Basically everything you see here. All right, so to start wrapping up, let's come back to that original problem. Again, I picked the geospatial problem. How do we extract 20 million buildings from satellite imagery in a workday? And that is possible because you can divide and conquer. And that is what batch is very good at. So you can subdivide your area of interest into small tiles. There can be thousands of them. And you can use a uniform grid and basically just like a cookie cutter, and it intersects with it. And that's your smaller units that you can process at the same time. I mean, how the code works isn't important here, but you can also apply this to any other problem. It can just be text. It can be, in this case, it's imagery because it is extracted from satellite imagery. It can really be any data that you want to, divide up and process in parallel. So then after you've divided the data, you can count how many cells or things there are that you want to process in parallel. And that is going to be your number of batch child jobs, how large your batch array will be. And this all can run on Lambda. You can, if it takes some time, you can run it somewhere else, but I think Lambda isn't too bad for this. This is just the setup. So basically, right at the bottom of this timeline, after you've done the count, you submit all your batch jobs. And so you set up your jobs, including your arrays, dependencies, all those things, and then you submit it all in advance. So let's say you can run 1,500. Let's say that's your sort of capacity that AWS granted. You can have 1,500 instances running concurrently. Good luck paying that bill. It's going to be expensive. And in this case, let's say you can divide Germany into then 4,000 cells. So how that would look, it's just for interest, essentially how this process would look in the real world, the geospatial problem. You would have a batch job. So essentially it's that earlier diagram where you had job A, so image download is job A with A0, 1, 2, etc. And there's an end-to-end dependency between that and the deep learning part. The deep learning part basically takes your satellite images, it runs a deep learning algorithm over it, and it extracts a raster or essentially an image, but it's just gonna look at like hotspots where buildings are. And then the vectorization step will trace the outlines essentially, and that's when you get like think about Google Maps if you use it, and it's like not on satellite view, the buildings that you see there. So at that point you have all of them, but they're not merged yet. So then you get to the merge step, but before that you have to just wait. So you can have a full waiting dependency between the two of them. And then you can merge or start merging all of them together. You can, in some cases, do that in a single step. In this case, you would still have to look at its neighbors and do some maths to do that. And then right at the end, you can have an export to export your results, whatever it may be. So basically, if everything gets set up between 8 and 9 in the morning, you can sit back and relax, and all of this will be done by batch, and right at the end of your working day, you will have the results. So last two slides, batch best practices. The first one is to optimize Docker images, because I have worked with 20 and 30 gigabyte Docker images in size, and it's not nice to work with because you have to download it, and AWS has a very fast network, that's not the problem, but your hard drive is usually the bottleneck. So lazy loading is important, layer optimization, we're not gonna dive into that. It just means that you can optimize the way you write a Docker file. And on the left, you can actually see there's research that was done on that, and they found that the data that is copied accounts for 76% of the container startup time, which can be several minutes. And of that, only 6.4% of the data is really needed to get going on some task that you need right at the start, So why copy everything across if you can incrementally copy it as you need it? So that's the first. And then the second is you can start small and then just prepare for scale later. Think things like quotas, because AWS, for those of you who's run into quota limits before, you have to request these increases ahead of time. And then you should also monitor for bottlenecks. You can easily get bottlenecks when running over 100 or 1,000 instances. I've even seen cases where S3 can be a bottleneck. If you have too many concurrent read requests from the same path on S3, then you can actually run into problems there. You can only have, I think, 5,500 read requests to a specific file or path on S3 per second, which sounds like a lot, but with Batch, it really isn't that much. And then you should also, like I mentioned earlier, diversify your instances. Mix new and previous generation instances if needed. If you need a graphics card attached to the instance, use G4, G5, and G6 instances, and have some backup capacity available. And then just something very advanced, but just to show that Batch is really powerful as well. It's simple yet powerful. You can have something called a multi-node parallel job. This just means that you run single jobs that span multiple EC2 instances. So it's proper distributed computing. Think distributed model training if you want to not just have one GPU to do your AI model training. If you want to have a few hundred, you could, in theory, do that with Batch. And it supports industry frameworks that you would use for things like that. So yeah, just before the last slide, or this is basically the last slide, the session content is, as I mentioned, available at that QR code. You'll find things like the slide deck that I've presented now. There's the AWS Batch user guide if you're interested in getting started with Batch. There's also a tutorial, which is quite cool, to teach you how to do batch array job indexing. So I think in there they make you read from a shared text file or something, and then you can see how each job processes a specific line. And then there's also a workshop, if you have access to an AWS account, that you can run yourself to do a deep dive of Batch. And with that, I'm done. Thank you. And yeah, if you have any questions, let me know.